A very good morning, everyone. So I'd like to thank the organizers for providing me with this opportunity to present my work. So this work is titled Localization and Delocalization in Cavity-QED Networks with Varied Connectivity. And this was done in collaboration with Manas and Amit, who was a postdoc here. Let me start with motivating why we are studying this. So self-trapping is a very interesting phenomenon, and it's an area of rich physics, and it's observed in several very interesting systems such as cold atomic Bose and condensates and photonic systems, both in experiments as well as in theory. But from our literature survey, we found that most of the systems, they address either a dimer or a 1D array, and there seems to be a gap in addressing the effect of connectivity on self-trapping. And intuitively, one would feel that there should be some effect of connectivity on self-trapping, right? And motivated by recent developments in developing such non-trivial networks and establishing coupling between distant qubits. For example, recently in 2021, there was a work done by a group in TFR, Vijay and Shumeru, where they established such coupling between non-distant qubits, and they kind of established a quasi all-to-all coupling setup. So now that we know that why we are studying this, let me give you a brief outline of our work. So we explore Cavity-QED network with varied connectivity, and we consider two kinds of connectivity. One is an all-to-all coupling, and then there's a finite-range coupling. And we also explore various local systems, such as harmonic oscillators, which is a linear system, and two nonlinear systems, which is the Jaynes-Cummings model and the Bose-Hubbard model. Now, what do we mean by local systems, and what is this network that we're talking about? So if you look at this network here, we have this circular lattice, and we have this red units on the circular lattice. Basically, we have periodic boundary conditions, and each of these units have some local Hamiltonian. And all these local Hamiltonians are connected by these blue lines. It's a schematic representation with some coupling strength J. So each of these red nodes, they have this HI as their local Hamiltonian, and there is this H coupling, which is the coupling between these nodes. So on the left-hand side, we have an all-to-all coupling setup where all the nodes are connected. And on the right-hand side, we have this finite-range coupling. Here I've shown a two nearest neighbor coupling setup. Now let's start with the harmonic network, which is a simple linear model. And we will initiate the system such that there are n-pop number of photons in the test cavity, which we call the I = 0 cavity. And all other cavities are kept empty. And we'll use this initial condition for the rest of the study, no matter what the connectivity be or the local Hamiltonian be. And we define some useful quantities to characterize the self-trapping behavior. One is this imbalance, which is P, which is basically the photon imbalance between the test unit and the rest of the system. And we also define this degree of localization eta, which is 0 when we have complete delocalization, and 1 when we have complete localization. Now, one would expect if you increase the number of number of units in the system, the photons in the test unit have more pathways to escape, and therefore we should see delocalized behavior. But that's not what we see. Rather, we see that when we increase the number of units from n = 2 to n = 50, n = 2 is this blue dotted line, we see complete delocalization, whereas n = 50, we see almost complete localization. And we plot this eta as a function of the number of the system size, and we see that for n = 2, which is 0, and it eventually saturates to n = 1 for high number of nodes and units. So this is a completely opposite behavior, and this entire thing is for all-to-all setup. I should have mentioned. We observe this in all-to-all setup. But what happens when we move away from this all-to-all configuration? We see that self-trapping is lost. If you can see, we plot eta as a function of d, which is the number of neighbors for this 50 unit system. And exactly at n/2 mark, we see that there is this transition. n/2, we should be, if you remember the diagram, since it's a circular network, if the number of neighbors is greater than this n/2, then we effectively have an all-to-all setup. Now, why does this happen? The answer to this lies in the energy spectrum of the system. So if you look at the energy spectrum, on the x-axis, we have the k modes, which is the momentum. And if you look at the right-hand side panel, which is for the all-to-all coupling setup, we see two things. First of all, the k = 0 mode is separated from the rest of the k modes, which are completely degenerate. And this energy gap between the k equals 0 mode and the rest of the k modes increases as we increase the system side. And this increased energy gap is what leads to this self-trapped state. On the other hand, if you look at the finite range energy spectrum, neither are these finite k modes degenerate, nor does the gap between them increase with increasing system size. Therefore, we lose this self-trapped behavior in the finite range coupling setup. Now let's move on to a nonlinear setup instead from the harmonic oscillators. So this is a Jaynes-Cummings network, Jaynes-Cummings model, which we get when we couple a cavity with a qubit, and the coupling is given by this term with an interaction strength G. So there have been studies where they established self-trapped states in a Jaynes-Cummings dimer in theory, and later it was established in experiments. And in 2020, Manas and Amit showed that by incorporating drive, they can achieve long-lived self-trapped states in such systems. So in our simulation, what we did, we took 5 Jaynes-Cummings units and we put 10 photons in the test unit. And we did some exact quantum numerics. So we see that for small, this is for all-to-all coupled system, the big plot. And we see that small interaction strength, we see that the system is delocalized. But for large interaction strength, we see that the system is localized. So now where does this effect of connectivity come in? If you look at the insets inside, the left-hand side inset is for an all-to-all connected system, and the right-hand side is for a nearest neighbor connected system. So in both the cases, we see this clear transition from delocalized state to localized state at some critical value of the interaction strength. But the role of connectivity is evident when you look at the small interaction strength region. For all-to-all network, we still have some finite localization, but for nearest neighbor, we do not have this. So this localization comes from the effect of connectivity. Now, these systems are extremely large, and it grows as powers of the system size. So it's effectively impossible to do exact quantum numerics for large systems. But since we are probing the effect of network connectivity, we need to solve for larger systems. And how we do it is we use semiclassical approximations where we decouple such correlators. And what that basically does is it boils us down the problem to solving 5n coupled nonlinear differential equations. On solving that, we've obtained this interesting phase plot where in the x-axis we have the interaction strength and y-axis we have the connectivity. And we see this clear transition from delocalized to localized system. Another interesting nonlinear network is this Bose-Hubbard network, where we have this on-site attractive potential. This system is also, the dimension of the system is still extremely large. And again, making it impossible to carry out exact quantum simulations. So again, we resort to semi-classical approximations. And we see some interesting things happening here. For example, if you look at the second plot, we plot this degree of localization as a function of the system size. Initially, the localization decreases, and it decreases till some critical value of this n, after which it starts behaving like the linear model. If you remember, for the linear case, eta was increasing this way with the increasing system size. So why does this happen? So the reason is, like, we have this attractive, the u is positive here, we put u equals j. So this attractive potential, I mean, although we are increasing the number of ways for the photons to escape, this attractive potential tries to keep the photons trapped. But beyond some n star, the system, the role of connectivity, I mean, here we have an all-to-all setup, all-to-all connected setup. The role of connectivity dominates this interaction strength. As a result of which, what happens is, since now the role of connectivity dominates the interaction strength, so this behaves like a linear all-to-all connected network, and we have this increasing self-trap, increasing localization with system size. Another interesting thing we see that is that when we increase the value of u, this critical n star, this critical value of n also increases. We have plotted the critical n star as a function of u in this inset, and we see that, and this behavior is expected because if we have greater interaction strength, it just means that we need more number of units to dominate the effect of interactions. We also have this. We also plot degree of localization as a function of d, where we do it for 50 cavities, And we see that for like small u, we see that the interactions, the localizations, degree of localization dips initially. This happens, I mean, initially we have good localization because of the attractive potential, but as we are increasing the number of connections, that is the number of neighbors, we're providing more pathways leading to more delocalization. But eventually, after beyond certain number of finite neighbors, it again starts behaving as a an all-to-all connected network, and that's why we again see this increase in degree of localization. But for extremely large U, this effect of finite neighbor is not that evident. It just falls down to this all-to-all value which we have here. And here also we plot this phase diagram for this Bose-Hubbard model, where we see a clear transition from delocalized state to localized state. Again, we have this on the y-axis, we have the connectivity. On the x-axis, we have the interaction strength. Now, one might think that this non-monotonous behavior that we see in the Bose-Hubbard model might be some effect of the semi-classical approximation that we did. But to establish that that was not the case, we solved the system with exact quantum numerics for a smaller system, and we see that this non-monotonous behavior is actually consistent in the quantum simulations as well. And to benchmark our semi-classical results, we do this, we compare the semi-classical results with exact quantum system for some feasible system size, and we see an extremely good agreement between the two. Like, although in the Jaynes-Cummings model, we see that the graphs don't quite overlap exactly, but the transition from delocalized to localized state is still consistent, and it's happened almost at the same value of G. Now, as I said before, that one of the reasons we were motivated to work on this was experimental developments, and we wanted to make sure that our work is experimentally verifiable, and it's robust to the artifacts that experiments introduces. One of those artifacts is disorder. Since it's not possible to design network elements with exact values, there will be some error bar. So we have to ensure that with these disorders, say 1% or 10%, we don't have 10%, that's too much, but we still showed it for 10%, that when we introduce our disorders, our results don't change. On the left-hand side plot, we have disorder in the cavity frequency. On the right-hand side, we have disorder in the coupling strength between the units. Another artifact of experimental setup is dissipative interactions. Although, like, from dissipative interactions, we see that eventually the system will decay, but for some reasonable time scale, we see this localization effect to be consistent also in dissipative systems. Let me end by summarizing what we did. We investigated the role of connectivity in this phenomenon of self-trapping. We investigated three networks. In the harmonic network, we had analytical solutions where we saw that self-trapped states for large networks. And the reason for this kind of a behavior was due to this near flat band like behavior for the harmonic network in the all-to-all coupling case. And we analyzed the behavior due to the interplay of interactions and connectivity for the Jaynes-Cummings and the Bose-Hubbard network. We also see non-monotonous behavior in the Bose-Hubbard network. And we established robustness to experimental artifacts. And also this work can be further extended by incorporating the effect of drive and dissipation and dissipation. With this, I would like to end. Thank you for listening.
Thanks, Tamoghna. We can take 2-3 questions. We have time. So, yeah.
Hello. Could you explain why for a periodic system you said if the number of neighbors is greater than n/2, it's essentially all-to-all coupling?
Yeah. So if you look at this network, like, see, if this is a network of like 8 units, right? So if I have, say, four nearest neighbors. So from here I have 2. So if I look at this cavity, this will connect to this and this as well, right? And from the right-hand side, it will again connect from this and this. So effectively, this cavity is connected to all other cavities. And this only happens when we have greater than equal to the seal of n by 2, to be exact.
Thank you.
How do you introduce the disorder, this delta variable?
Like, so we have this right. So we have this Hamiltonian, right? So in J, we introduce some uniform disorder in J with some say 1% or 2% disorder based on, and then we just simulate normally as we do. And similarly for like the cavity cup, like in omega C also we introduce disorder 1% or 10% over it.
Okay, yeah. So the disorder is in both this omega C quantities and also the connectivity.
Yeah, we showed in both, for both the cases we showed that it's robust. Like this on the left hand side we have for when we introduce disorder in this cavity frequency, and here when we show that this disorder in the coupling strength.
Thanks, Tamoghna.